anybody of you has some additions, please let me know, okay? And again, please don't kill me. So, who of you knows what an artificial neural network is? Okay, I will skip that. Who could explain this one? Not everybody. So this is the topology of one single neuron. What it does is, if it's in the input layer, it uses x1 to xn. Those are the input dimensions. And then multiplies the data points with the weights, sums it up, and passes it to a transfer function, to activation function, sigmoid, tanh, rectifier, whatever, for adding non-linearity to the neural network. And then you send the data downstream, so either to a downstream hidden layer, or if you are in the output layer, of course, then you are the output itself. If you are in a hidden layer and you are this neuron, then of course the upstream x1 to xn are coming from the output of the upstream layer. Okay? And basically a single neuron, so everything from x1 to the transfer function resembles in the same thing as linear regression. And if you would use sigmoid as activation function, you will end up with something similar than logistic regression. So a feed-forward neural network is nothing else than a stacked set of logistic regression models based on the sigmoid activation function. So how are those neural networks trained? So the first thing you have to, of course, evaluate how it is performing. And what you do is you basically set random values to the omega parameters. So those are that omega 1 to omega n parameters. And let's see here what this neural network is doing. For example, if x is 1 and y is 0, then you multiply 1 by 1, you obtain 1. And you send that 1 downstream to the other leftmost neuron, the red one. And the same values you send to the middle one. But the reason why there is a 2 is because the neuron adds up all incoming errors of the upstream layer. Okay? So that's how you do the forward path. It's basically nothing else than computing that function you see at the bottom. It's computing the individual values and multiplying that individual values with the omega weights of the neural network, and then sums it up, and then it passes that value to the activation function, which can be sigmoid or tanh or rectifier or whatever. In order to train your neural network, you do something which is called backpropagation. So you basically do the same step in the other way, in the other direction. So what you do is you compare the actual value the neural network is predicting against the value you want to observe. Because that's supervised machine learning. So for every data set you have a label or a target variable, and you can compare the thing the neural network is basically generating with the actual weights with the real value, and then you get a difference, and that's the error. And basically, if you sum up all the errors, you get an overall error of the neural network. And then in order to adjust those weights, you can take the first derivative of that function, and this will tell you the gradient you have to adjust your values in order to obtain a higher error. So it goes to the steepest direction, but to a higher error. That's the reason why there's a minus. If you have a minus, then it goes in direction of the steepest way to the lowest error. And then you have that symbol eta here. That's the learning rate. So you don't want to make big steps, you want to do little steps. And that's basically gradient descent. Who of you knows what gradient descent is? Okay, so basically the idea is that's convex function, so it's relatively clear that it will end up at W1, 0 and W2, 0. But gradient descent doesn't guarantee to find the global optima. So if you have a non-convex cost function, then just be aware of that. So basically it starts and it goes down until it finds the lowest point. So that's the cost over the parameters W. Okay, that's that surface. And now we come to parallelization. So there are 4 ways of parallelize such training of a neural network. So that's inter-model parallelization, data parallelism, intra-model parallelism, and pipeline parallelism. And I will just cover all those 4 now. So inter-model parallelism is you basically have model A on model B and model C. They can have different parameters, different topologies. So for example, the activation function type is a parameter, the number of layers is a parameter, the number of neurons per layer is a parameter, the type of the layer is a parameter. You can have a feed-forward layer, a convolutional layer, LSTM layer, autoencoder layer, or whatever. So the whole neural network topology is basically defined through a vector, and that's basically one vector per model. And if you have, let's say, if you consider infinite types of models, then you have a hyperparameter space you can explore. And you want to find a good vector for that hyperparameters. You want to find a good number of layers, neurons, type of activation functions, learning rates, L1, L2 regularization. And that's the reason why you have model A, B, C, or model 1000, model 10,000. And what you then basically do with intermodal parallelism is you train such a model on a separate node. And in Spark, you can kind of automate this. That's the most basic one. Okay, there's no big communication going on between the models. And they are basically trained with the same data set. Okay, that's one. Okay, second, data parallelism. Some people call that Jeff Dean style parameter averaging, because Jeff Dean came up with that idea. So you have model A and model A and model A, and you deploy those identical models on each node. But then what you do is you show each model only a fraction, a subset of the data, and then you regularly send the learned parameter space omega to a parameter server. That's one option. There's also an option to have communication between the models itself, but that doesn't matter. But you send the parameters you have learned on a particular batch somewhere, and those are collected, and then they are just averaged. And then they are sent back to the executors. And that way you can train a neural network in parallel, but still each node executes one single neural network, only each node is showing a different subset of the data to the neural network, and using that parameter server, the learned parameters, omega, are synchronized, using just by a simple averaging function. There are 2 ways of doing that. You can either do it synchronously. That means the next iteration waits until every model has finished the training of each iteration, and the model, the parameter server has updated or sent back updated values for the omega parameters. Or you can also do it asynchronously, and that basically means that outdated parameters might be sent out to the network. But there's a YouTube video on Cafe on Spark, and they are basically telling that this is not a big issue. I'm a bit concerned. I wouldn't do that, but they have done that. So I would always let every model wait in the hope that the amount of time each model needs for training is more or less the same, because the amount of data is the same and the topology, the configuration of the model is the same. So I would expect quite equal runtimes per iteration. And the next thing you can do is intra-model parallelism, because a neural network has many points where you can run operations in parallel. That means you can divide up the neural network into different parts and then distribute that to the Spark workers and then show each part all data. Or of course you can also combine this with a data parallelism approach. Then you would basically, for example, have 6 or 12 or 24 nodes. Okay? You can combine basically all those approaches. And there are many points where you can do it, but I've just identified those ones for you. So you have to calculate the input to the neuron and multiply it with the weight, and those variables are independent of each other. So you can basically, in theory, run one neural network per input parameter, but of course you would kind of group them together, and if you have 10, then maybe 5 on one machine, 5 on the other, but that's up to you, or basically that's up to the library which is running on top of Apache Spark. So, and then the last thing is pipelined parallelism, which basically works as follows. So that's input data, that's a sequence of input data. And in the first step, you just execute the first layer. So what you do is you multiply the input data x with the weight of the first layer. And once this is done, you take the next item in the data set. And now you can run in parallel. You can now calculate again for the second data set the multiplication of the input value with the weight in the first layer, and in parallel on another machine or another core, whatever, you can calculate the output of layer 1 multiplied with the weights of the second layer. Okay, that's the way of how to do pipelined parallelism. And so just as a reminder, that's how a Apache Spark topology looks like. You have one driver, and then you have executors, and they are able to communicate with each other through broadcasts. And now I will show you how deep learning for J is doing this. So you have a multi-layer network configuration object which takes as a parameter you have a multi-layer network object which takes as a parameter a configuration object, and the configuration object is the configuration of the neural network, which contains all the layers and number of neurons and type of activation functions, learning rate, L1, L2 regularization. And if you are executing the first line, you obtain a neural network which can run in parallel on one machine. So on this machine, that network would run 8-way in parallel because I have 8 cores. But if you are using the second line, you need 3 parameters. Conf is obvious. Then SC is also obvious. That's the Spark context. And the third one is TM, and that's just an instance of a parameter averaging training master. That's the component which I've shown before. Let's go. That's parameter server. So they are using the broadcast function of Apache Spark to communicate with that parameter server, and basically that means that deep learning for J using the second line is employing data parallelism. But there is a bit more. Deep learning for J is based heavily on a library called ND4J, which is somehow the NumPy equivalent for Java and Scala. It's also from the Deep Learning for J project. It already runs 2 times as fast as NumPy on a CPU. And by just setting one parameter, you can tell ND4J to use a GPU. And that adds intra-model parallelism to Deep Learning for J. So the next thing I've had a look at, it's SystemML. Have somebody heard about SystemML? Okay, at least some. It's declarative machine learning, and the idea is that an optimizer creates execution plans on the code based on statistics of the data. It's an IBM research project which has been open sourced 2015. It's systemml.apache.org, and that's the way how to write up algorithms in SystemML. So this is R code. So what do you think you have to do to execute that on SystemML? Nothing. So the idea is SystemML supports a subset of R, so you can implement your algorithms in R, a syntax you might already be aware of. And you see here, for example, there is some transpose U matrix multiplied with W times U matrix multiplied with V minus X plus lambda times V. And SystemML is aware of the size of those matrices and vectors and chooses for an optimal algorithm and therefore for an optimal execution plan. Here are some benchmarks. And basically, low-level operators can, for example, run on a CPU core, on a single machine, or on a GPU, or as a parallel Spark job, or as a parallel MapReduce job. And that's all what the optimizer basically decides. And the cool thing is, SystemML has added support for deep learning recently. And all those deep learning algorithms are implemented in the SystemML domain-specific language. So they did not change the engine at all for achieving this. And that basically gives you data parallelism, because the underlying engine decides on parallel execution. So basically, if you have a matrix multiplication, which you of course have during neural network training, that matrix multiplication is running in parallel on a Spark cluster. And of course it has also intra-model parallelism, because the matrix multiplication which makes up the model is running in parallel on the Spark cluster. So now TensorFlow. So now I'm leaving my Terra where I'm kind of an expert. So I've found 2 things. I've also validated that with somebody else. There are 2 projects for TensorFlow on Spark. The first one is TensorFrames, which basically just gives you the possibility to access Spark data frames within a TensorFlow graph. And the only thing what you can do with that is inter-model parallelism. So what you can do basically, you can run the same graph multiple times with different parameters, and that can be used for hyperparameter space exploration or of course for parallel scoring. Then there is TensorSpark, and TensorSpark is one step further. So TensorSpark implements the parameter server on the Spark driver as of now. So there are plans to use Tachyon and other projects for doing that, but at the moment it uses the Spark driver as parameter server. And the only thing what you have to do, of course, you have to install TensorFlow on each and every worker. But then basically you can submit a TensorFlow job just using Spark Submit and submit the Python script, and then that works. And that, of course, is data parallelism, which is much more interesting than only intermodal parallelism. The last thing, oh, I'm way too fast. Anyway, the last thing I want to show you is Caffe on Spark. And I thought they are doing some basic intermodal parallelism, but actually they came up with a nice idea. So they are doing data parallelism, but they don't need a parameter server. So they have a model synchronizer which runs inside Caffe and which can use inter-process communication over the network in order to update the parameters. So that's on the same level like deep learning for J and Tensor Spark. So that's actually quite nice for those who want to use Caffe. I haven't covered H2O in this. So somebody in the last talk told me that H2O now has also support for GPUs and all sort of neural network topologies. And there's sparkling water. And I guess that it's also data parallelism what they are supporting, but that's something I would have to find out. Okay, I'm already done. So you can... Okay, you didn't check. Okay. Yeah, so the only thing I know sparkling water is the Spark implementation of H2O. But at the point where I have had a look at it, it was only supporting feed-forward neural networks and it wasn't supporting GPUs. And therefore, I had a look at deep learning for J. And now I recently discovered SystemML, that it has support for deep learning. And now I'm trying with SystemML because I think deep learning for J and SystemML are first-class citizens on Apache Spark. And the other thing is just a way of executing scripts in parallel somehow. But anyway, Tensor Spark seems to work quite well on specific data types, and on other data types the problem is the parameter server. So the synchronization on the parameter server causes the whole system not to scale out linearly anymore. Yeah, so that's basically it. Don't kill me. Just if you have questions, I try to answer them.
My first question is, does it work? So, I mean, training a neural network and you have data parallelism obviously gives different results because the network is converging in a different way to its final destination. So, is it actually giving the same results, or how does it, do you have any figures? How far does it scale? When does the parameter server gets the bottleneck? Do you have some figures or some... Yeah,
I can tell you two things. So the first thing is it doesn't diverge because it's regularly updated. So the thing is they are trained using batch gradient descent. No, it's mini batch gradient descent. So that means they are showing only a couple of examples to neural network, and then they do an update round. So that's the answer to the first question. The second one, this whole idea was inspired by the Google Brain, and that scaled to 16,000 cores and 1,000 nodes. So that's kind of a proof that the general approach of synchronizing and updating the parameters on a central parameter server works.
So maybe one to get it straight for me. So you say that the process of training the network will not find different local minima in the parameter space than doing it just on one machine? It
will find. Even if you train the same neural network with the same data a second time and you are not setting the seed, it will find it different. Okay, right. That's anyway the problem, no?
So, am I right in assuming that this is just an experimental implementation without any mathematical certainty behind it? I mean, the method, the parallelization of the data, because I had the same doubt. Okay. If you have a strongly symmetrical neural network, you will choose a say, a pathway of weights for the network, given a certain amount of data. But you could turn it and move it and find another pattern which is exactly as good as this. If you have perfect symmetry, at the end, you average over all the data, you get flat network. So you didn't learn anything. So is there any mathematical result behind it motivating this approach, or any technique to break the symmetry, or nothing?
That I don't know. So the only thing I know is that it works based on the paper Jeff Dean published on the Google Brain, and that was inspiring this guy who is called Adam Gibson, who implemented it on deep learning for J. And there are now mathematical proofs, I think, but there are experiments which show that it works.
Experimental proofs,
yeah.
Not, okay.
Yeah.
So, hi, thanks for an interesting overview. You mentioned this system ML, and perhaps I missed something, so perhaps you could explain a bit more about the declarativeness of system ML. When I looked at the code, it seemed to be rather procedural with that while loop and a lot of variable assignments and so on. So it seemed to be not much more declarative than any MATLAB program, for instance.
Good point. So I think they are working on DSL for Python, which they are aiming to support the recognition of while loops and transforming that while loops into something different. I'm not really aware of that. DSL at the moment is recognizing that while loop and transforming the whole body into something different. I don't think so. But there are ideas and things are going on into that space. Yeah. The declarativeness is more on the level of the operators, and so the low-level operators, whether you do a matrix multiplication using a local machine, using a certain algorithm, or you do it in a parallel fashion on Spark. That's the thing the optimizer kicks in.
Like MATLAB.
Is it? So you're a MATLAB fan, huh? But it's open source. MATLAB is quite expensive. No? So I won that one.
I want only to add to the previous question that there are mathematical foundations. You have to look at Léon Boutou at Facebook. He has a 100-page paper about stochastic gradient descent and large-scale deep learning. So there are mathematical foundations.
Okay, can you please repeat the name of the...
Léon Boutou.
Okay, perfect.
It's with Jan LeCun, also one famous.
Perfect, thank you. Okay.
Hi, can you put back the benchmark, because you go really quick on the benchmark, and talk a little bit about the results and maybe the reason why we have some differences, if you know why.
Okay, so the first thing that R crashes, that's normal, it always crashes. Any R fans in here? Oh, okay. So I like it, but it always is very slow and sometimes crashes, okay, out of memory. Then you have MLlib. That time they have produced that chart, the standard, so there is no Spark ML benchmark now out. I assume it won't be much faster, Spark ML. Spark ML makes use of Catalyst and Tungsten because it uses datasets and data frames, but there is no optimizer on the execution plan of the mathematical operations. So also in Spark ML, you have a fixed execution plan, whether you are multiplying a small matrix with a big one or a big one with a small one. SystemML can take this into account because SystemML knows the sizes of the vectors and matrices it operates on and therefore chooses an optimal execution plan. And that's the reason why SystemML is faster, and you see it's significantly faster on the 12 GB dataset. And also they stopped MLlib after 1 day and just said, okay, it takes more than 1 day on the 120 GB dataset. That's basically where they are calculating, they are doing a matrix factorization using ALS, alternating least squares. That's basically also the code about. And that's the ALS implementation of MLlib took on the 120 GB data set more than 1 day, and in system ML less. Yeah. Okay, no more questions?
Since there are no more questions, can I ask something related to your other talk?
Of course.
So can you use two vibration signals, for instance? So I guess you were using only one signal.
Aha.
Can you mix 2, 3 in the same?
Yeah, you can mix as many as you like. Basically, irrelevant data normally is automatically downregulated in a neural network. But I would guess if you are mixing too many, then an anomaly on a single sensor will just be below the noise threshold. But if you are measuring multiple vibration sensors and they are all connected to the same physical thing, then I guess that you would even increase accuracy of that anomaly detector.
Thanks.
Okay. Okay, so I gave you 8 minutes of your lifetime. So enjoy.